NENOMATICA, where mathematics meets YouTube excellence. Welcome to Reciprocal Equations. In this lesson, we'll learn how to identify positive and negative reciprocal equations and how to solve them efficiently using a substitution that reduces the degree. First, the idea. A polynomial f of x of even degree is positive reciprocal if replacing x by 1 over x gives the same equation after clearing denominators. It is negative reciprocal if replacing x by negative 1 over x gives the same equation after clearing denominators. There is a quick symmetry test on the coefficients. For positive reciprocal equations, the coefficients read the same forwards and backwards, like a mirror. For negative reciprocal equations, the end coefficients match, but the near-end pair have opposite signs. Let's verify a classic example of a positive reciprocal equation. Consider ax to the fourth plus bx cubed plus cx squared plus bx plus a equals 0. We will replace x by 1 over x, simplify, and then multiply through by x to the fourth to clear denominators. We should recover the exact original equation. Now, let's verify a negative reciprocal example. Consider ax to the fourth plus bx cubed plus cx squared minus bx plus a equals 0. Replace x by negative 1 over x, simplify, multiply by x to the fourth, and rearrange. You get exactly the original equation back. That confirms it's negative reciprocal. How do we solve these efficiently? For even degree n equals 2k, divide by x to the k. Then group mirror pairs. For positive reciprocal equations, set u equals x plus 1 over x. For negative reciprocal equations, set u equals x minus 1 over x. The key identities reduce higher powers of x plus or minus 1 over x into polynomials in U, turning the problem into a simpler quadratic in U. A reciprocal equation has symmetric coefficients reading from the outside in. For a positive reciprocal of even degree, the first equals the last, the second equals the second from the end, and so on. For odd degree reciprocals, one of the roots is plus 1 or minus 1. Negative reciprocal equations use alternating signs with symmetry and cannot be of odd degree. Let us work a complete example. We will solve the equation 2x to the fourth plus 5x cubed minus 14x squared plus 5x plus 2 equals 0. First, notice the coefficients are symmetric. 2, 5, minus 14, 5, 2. That tells us this is a positive reciprocal equation of even degree. Step 1. Because the degree is 4, we divide every term by x squared. This centers the equation around the middle power so that conjugate terms can be grouped. Step 2. Group the symmetric terms together. The x squared term pairs with 1 over x squared, and the x term pairs with 1 over x. Step 3. Make the substitution. For positive reciprocal equations, let u equal x plus 1 over x. Then x squared plus 1 over x squared becomes u squared minus 2. Substitute both into the grouped equation. Step 4. Solve the quadratic in U. 2u squared plus 5u minus 18 equals 0 factors, as 2u plus 9 times u minus 2 equals 0. Therefore, u equals 2, or u equals negative 9 over 2. Step 5. Back substitute using x plus 1 over x equals u. Multiply both sides by x to get x squared minus ux plus 1 equals 0. We now solve this for each value of u. First, when u equals 2, we have x squared minus 2x plus 1 equals 0, which factors as x minus 1 quantity squared equals 0. So x equals 1, a double root from this branch. Next, when u equals negative 9 over 2, we get x squared plus 9 over 2x plus 1 equals 0. Multiply by 2 to clear the fraction, and solve using the quadratic formula. That gives x equals negative 9 plus or minus the square root of 65, all over 4. Final answer. The solutions are x equals 1, and x equals negative 9 plus or minus the square root of 65, all over 4. This example demonstrates the full algorithm for solving positive reciprocal equations of even degree. Our equation is 2x to the fourth minus 13x cubed plus 24x squared minus 13x plus 2 equals 0. Notice the coefficients are symmetric. 2, negative 13, 24, negative 13, 2. This symmetry suggests pairing x terms with reciprocal terms. Step 1. Because x equals 0 is not a root, we divide both sides by x squared. This rewrites each term, pairing x powers with reciprocal powers. After simplifying, we collect like forms. Step 2. Group terms with the same coefficients to expose the symmetry. Write 2 times the quantity x squared plus 1 over x squared, minus 13 times the quantity x plus 1 over x, plus 24 equals 0. Now use the identity x squared plus 1 over x squared equals the square of x plus 1 over x minus 2. Step 3. Let y equal x plus 1 over x. The equation becomes 2y squared minus 13y plus 20 equals 0. Now solve the quadratic for y using the quadratic formula. We get y equals 4 or y equals 5 halves. Step 4. Solve for x from each y value. 4y equals 4. We have x plus 1 over x equals 4, which gives x squared minus 4x plus 1 equals 0, yielding x equals 2 plus square root of 3, and x equals 2 minus square root of 3. 4y equals 5 halves. We get x plus 1 over x equals 5 halves, which is equivalent to 2x squared minus 5x plus 2 equals 0, factoring as 2x minus 1 times x minus 2 equals 0, giving x equals 1 half and x equals 2. In this example, we will solve the quadratic equation x to the 4th minus 3x cubed minus 6x squared plus 3x plus 1 equals 0. We will follow a reciprocal style strategy that turns this into a quadratic in a clever substitution. Here is our step plan. 1. Divide by x squared assuming x is not 0. 2. Group terms to reveal a pattern. 3. Use the identity for x minus 1 over x to relate squares. 4. Substitute y equals x minus 1 over x and solve the new quadratic. 5. Back substitute to get all 4x solutions. Step 1. We first check that x equals 0 is not a solution, and then divide the entire equation by x squared. This lowers the powers and reveals symmetry between x and 1 over x. Step 2. Group the squared pair and the linear pair to set up an identity. Left parenthesis x squared plus 1 over x squared right parenthesis minus 3 times left parenthesis x minus 1 over x right parenthesis minus 6 equals 0. Step 3. Use the identity left parenthesis x minus 1 over x right parenthesis squared equals x squared minus 2 plus 1 over x squared. So x squared plus 1 over x squared equals left parenthesis x minus 1 over x right parenthesis squared plus 2. Substitute that into our grouped equation and combine constants. Step 4. Let y equal x minus 1 over x. Then the equation becomes y squared minus 3, y minus 4 equals 0. This factors as left parenthesis y minus 4 right parenthesis times left parenthesis y plus 1 right parenthesis equals 0. So y equals 4 or y equals negative 1. Step 5, case 1. If y equals negative 1, then x minus 1 over x equals negative 1. Multiplying both sides by x gives x squared plus x minus 1 equals 0. Using the quadratic formula, we get x equals negative 1 plus or minus square root of 5, all over 2. Step 6, case 2. If y equals 4, then x minus 1 over x equals 4. Multiplying both sides by x gives x squared minus 4, x minus 1 equals 0. Solving, x equals 2 plus or minus square root of 5. Finally, we gather all 4 roots. The solutions are negative 1 plus or minus square root of 5, all over 2, and 2 plus or minus square root of 5. In this lesson, we will solve the equation, open parenthesis, 2x squared minus 3x plus 1, close parenthesis, times open parenthesis, 2x squared plus 5x plus 1, close parenthesis, equals 9x squared. We'll follow a clean substitution strategy that turns this quadratic into 2 simple quadratics. Step 1. First, we check whether x equals 0 is a solution. If we plug in x equals 0, the left side becomes 1 times 1, which is 1, and the right side is 0. So 1 equals 0 is false. Therefore, x is not 0. That means we can safely divide both sides by x squared. We'll distribute 1x into each factor on the left. Step 2. Notice the symmetric expression, 2x plus 1 over x, appears in both parentheses. We can group terms around that quantity. Now define a new variable y. where y equals 2x plus 1 over x. Substituting y, we get open parenthesis y minus 3 close parenthesis times open parenthesis y plus 5 close parenthesis equals 9. Step 3. Expand and simplify to solve for y. We get y squared plus 2y minus 15 equals 9. Move 9 to the left to get y squared plus 2y minus 24 equals 0. This factors into open parenthesis y plus 6 close parenthesis times open parenthesis y minus 4 close parenthesis equals 0. So y equals negative 6 or y equals 4. Step 4. Back substitute y equals 2x plus 1 over x and solve each quadratic in x. First case, y equals negative 6. That gives 2x plus 1 over x equals negative 6. Multiply both sides by x to get 2x squared plus 6x plus 1 equals 0. Solve with the quadratic formula to get x equals negative 3 plus or minus square root 7 over 2. Now second case, y equals 4. That gives 2x plus 1 over x equals 4. Multiply by x to get 2x squared minus 4x plus 1 equals 0. Solve to get x equals 2 plus or minus square root 2 over 2. Collecting results. Our solution set contains all 4 values. In this example, we solve the equation open parenthesis 6 minus x close parenthesis to the fourth plus open parenthesis 8 minus x close parenthesis to the fourth equals 16. We'll use an average substitution to simplify the symmetry, then expand, cancel, and factor to finish. Step 1 is a change of variable using the average of the two bases. Define y as the average of the two bases, open parenthesis 6 minus x close parenthesis, and open parenthesis 8 minus x close parenthesis. That gives y equals fraction 6 minus x plus 8 minus x over 2, which simplifies to 7 minus x. From this, we can also write x equals 7 minus y. This single substitution will make the 2/4 powers symmetric around 0. Now substitute x equals 7 minus y back into the original equation. We replace every x by 7 minus y. That gives open bracket 6 minus open parenthesis 7 minus y close bracket to the fourth plus open bracket 8 minus open parenthesis 7 minus y close bracket to the fourth equals 16. Simplify the brackets to get y minus 1 to the fourth plus y plus 1 to the fourth equals 16. Next, expand each binomial to the fourth power using the binomial theorem. For open parenthesis, a plus or minus b close parenthesis to the fourth, the pattern is a to the fourth plus or minus 4 cubed b plus 6a squared b squared plus or minus 4ab cubed plus b to the fourth. So, expanding y minus 1 and y plus 1, then adding, we get a lot of cancellation, the odd powers cancel. That leaves 2y to the fourth plus 12y squared plus 2 equals 16. Move 16 to the left and divide by 2 to obtain y to the fourth plus 6, y squared minus 7 equals 0. Now factor this biquadratic by letting u equal y squared. You can factor u squared plus 6, u minus 7 as open parenthesis, u minus 1 close parenthesis times open parenthesis, u plus 7 close parenthesis. Substituting back u equals y squared yields open parenthesis, y squared minus 1 close parenthesis times open parenthesis, y squared plus 7 close parenthesis equals 0. So either y squared minus 1 equals 0, giving y equals plus or minus 1, or y squared plus 7 equals 0, which has no real solution. Finally, substitute back, using x equals 7 minus y. If y equals 1, then x equals 7 minus 1 equals 6. If y equals negative 1, then x equals 7 minus negative 1 equals 8. So the solutions are x equals 6 and x equals 8. Quick check. Plugging in x equals 6 gives 0 to the fourth plus 2 to the fourth equals 16. Plugging in x equals 8 gives 2 to the fourth plus 0 to the fourth equals 16. Both satisfy the equation. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.